Have you ever thought about a mathematical crystal ball? I mean, an equation that could look at a system right now, like a growing population or even just a cooling cup of coffee, and tell you exactly where it's going to end up without ever needing a clock? Well, that's what we're talking about today. We're diving into the pretty amazing world of autonomous differential equations. So let's really frame our whole conversation around this one big question. What if an equation could reveal a system's ultimate destiny just by looking at what it's doing right now? No need for future data, no complex simulations, just a snapshot of the present. This is the incredible predictive power we're going to unpack. So, what's the secret sauce behind this predictive magic? Well, it all boils down to one simple, elegant idea. The system's evolution depends only on its current state, not on the specific moment in time it happens to be. Okay, so here's the formal definition. An autonomous differential equation is one where the rate of change, that's our dy dx, is a function only of the system's current value y. Now look really closely at the right side of that equation. Notice what's missing. The variable x, time, is totally absent. That one little omission is the key to everything. This slide really lays it all out, side by side. On the left, you've got dy by dx equals y times 1 minus y. That's autonomous. Its rate of change only cares about what y is right now. But on the right, dy by dx equals sine of x. Well, that's non-autonomous because its rate of change explicitly depends on x. You're looking at two fundamentally different kinds of systems. So, if we want to predict a system's final destination, the very first thing we have to do is find its potential resting spots. I mean, where could it, in theory, just stop and stay the same forever? These are its crucial points of balance, its equilibrium. An equilibrium point is just a value. We'll call it y sub 0, where the rate of change hits exactly 0. It's like the system's evolution flatlines. If the system ever lands perfectly on this value, it's going to stay there for good, in perfect balance. But, and this is a huge but, not all these balance points are created equal. Some of them act like they're pulling the system in, while others are actively pushing it away. This behavior is what we call stability. And it's kind of like an invisible force that guides the system's destiny. So how do we figure out if it's a push or a pull? Well, we have a super handy tool for that, the derivative test. Think of the derivative as telling you the trend right around that equilibrium point. If the derivative is negative, it means if you get nudged away, the system pushes you back. That's stable. If the derivative's positive, a little nudge sends you flying further away. That's unstable. And if it's 0? Well, the test can't tell us, and we have to dig a little deeper. A stable equilibrium is pretty intuitive. It acts just like a magnet. If you start the system anywhere near this point, it's inevitably going to get drawn toward it over time. It's a final destination. And then you have an unstable equilibrium, which is the complete opposite. It's a repeller. If you start the system even a tiny bit away from this point, it gets pushed further and further away, never to come back. Think of it as a point of no return. All right, now for the really cool part. Here's how we can see all of this in action without solving a single complicated equation. It's a technique called phase line analysis. First, you find your equilibrium points, where the rate is 0, and just pop them on a vertical line. Then, you test the spaces in between. In any given region, is the rate of change positive or negative? If it's positive, the system's increasing, so we draw an arrow pointing up. If it's negative, it's decreasing, arrow points down. And just like that, this simple diagram becomes our crystal ball, showing us the long-term behavior from any starting point. It's awesome. And this leads us to what is basically the golden rule here. Always analyze equilibria first, before attempting separation. Why? Because understanding the stability, knowing the long-term behavior, that gives you so much incredible insight before you ever get stuck in the weeds of the algebra. Okay, let's keep going. So, we've used our crystal ball to see the final destination. But what if we want a detailed map of the entire journey? What if we want to find the exact solution path? For that, the main tool in our toolbox is a technique called separation of variables. And honestly, the name pretty much says it all. The whole goal is to just shuffle the equation around so that all the y stuff is on one side and all the x stuff is on the other. So the process looks just like this. We basically treat dy dx like a fraction. We move everything with the y over to the left side with the dy, and everything with an x, in this case just the dx, over to the right. Once they're separated, all we have to do is integrate both sides. And that integration, that's what gives us the explicit formula connecting y and x. It's the roadmap of our system's journey. Now, a lot of the time, we don't just want
any map, right? We want the map for our specific trip, starting from where we are. That's called an initial value problem, or an IVP. That one little piece of information, our starting point, lets us solve for that constant of integration and lock in the single, unique solution curve that our system is actually on.
I know this can all feel a bit abstract. When am I ever going to use this? But the truth is, these powerful equations show up all over the place in the real world. Let's look at a couple of classic examples.
First up, let's talk about logistic growth. This is a fundamental model in biology, and it describes how a population grows when its resources are limited. Unlike simple exponential growth, it can't just keep growing forever.
And here is the equation itself. The rate of population change, dp over dt, it depends on two things. First, the current population, p. More rabbits make more rabbits. And second, this other term, m minus p, which really represents the room left to grow before it hits some kind of limit. So when the population is small, growth is fast, but as p gets closer and closer to that maximum value m, the growth rate just grinds to a halt. And that number, m, is what we call the carrying capacity of the environment. Does that sound familiar? It should. It's the stable equilibrium point for this whole system. It doesn't matter where the population starts. As long as it's not zero, it will always head toward this value m. Okay, another classic example. Newton's law of cooling. This describes something you experience literally every day. A hot cup of coffee cooling down, or a cold drink warming up to room temperature. The equation says the rate of change of the object's temperature, T, is proportional to the difference between its temperature and the temperature of its surroundings, Tm. And guess what? That surrounding temperature, Tm, is, yep, you guessed it, the stable equilibrium. That coffee is always going to end up at room temperature. So let's wrap this all up. What's the big takeaway? It's that these autonomous equations, the ones that depend only on a system's current state, have this incredible superpower. We can actually predict their future, their final destination, without ever having to solve for the exact path. All we have to do is find their balance points and check if they're stable. And as we've seen, this isn't just some math curiosity. It's the hidden logic running things all around us, from population growth to your morning coffee. And that kind of leaves us with a final thought to chew on. Now that you have these tools, now that you can look at a system's rules of change and predict its ultimate destination, what other things out there, in finance, in chemistry, maybe even in social dynamics, what other phenomena might be hiding one of these powerful autonomous equations at their core?